All right, so this is, for example, almost cell phones. You have these cellular system, you have base stations spread out. They have to talk to a central office or connect to the telephone switching system in some way. So they have these high data rate communications links that connect the base stations and connect the parts of the system to other parts of the system. So this is a very common frequency range to do this because there's lots of bandwidth available up here. And this is typically done around 6 gigahertz or so. There's a bunch of channels, a bunch of frequencies in which this happens. You could recognize these because you're hanging off of cell towers. They're typically dishes or horns. They're about this big. And, if you look for them, you will quite often see them. Satellite comms. And here I'm talking about things typically, I don't know, 10 gigahertz, 12 gigahertz. A satellite communications application, which I think all of you are familiar with, is direct broadcast satellite. Personal television at your door using dishes are about this big. That's done at about 12 gigahertz. That's certainly the regime that I'm talking about. And then, all things millimeter wave. So millimeter wave is an area which is really taking off these days for a bunch of reasons. I'll just list 2 here. There's many ways in which this area is currently kind of exploding in interest. One, just to give you an example, 77 gigahertz radar. Anybody know what the 77 gigahertz radar is used for? Or an application of this? Vehicle radars, anti-collision radars on vehicles. So you can right now buy a Toyota, I can't remember the model, but you can buy a Toyota that has 77 gigahertz radar built into it that's meant to provide some indication when you're getting too close to somebody else. But this frequency range is used for a lot of such applications. Another one, 60 gigahertz ISM. ISM stands for Instrumentation, Scientific, and Medical. It's license-free spectrum. Future Wi-Fi systems, some already available, will be using this chunk of spectrum because there's enormous bandwidth available at 60 gigahertz. And so there's a lot of research and corporate development as well happening at 60 gigahertz to implement these very high data rate Wi-Fi-like systems. So this is the domain of application that I'm talking about. Questions? All right. So I promised a lecture on microwave receiver design. So we should say, what is a receiver? You would be amazed, especially on my section of Durham Hall, how many different answers you get to this particular question. So I should be clear on what I mean by what is a receiver. Well, you know, you got some gadget that's got an antenna, and then a whole bunch of stuff, and then a detector, or maybe a digitizer, an analog to digital converter, right? So my definition of receiver is everything between an antenna and the thing which is either doing detection or digitizing the signal and then doing something sexy in the analog and in the digital signal processing domain. Right? The detector could be an AM detector, could be an FM detector. I mean, those are things you probably have encountered before. And certainly if you digitize a signal, there's all kinds of things you can do with that. No, I should not exclude radar. You can detect radar pulses and things like that in the analog domain. So I'm interested in everything between the antenna and the detector. The 3 primary things we're going to talk about, the 3 primary things that define kind of what a receiver is, I would say, are 3 things. One is gain. One is sensitivity. And the third thing is selectivity. Most receiver designers, whether they realize it or not, end up thinking, especially in terms of initial stages of system design, about these 3 things. How much gain do I need? How much sensitivity do I need? I think you have some feeling for what sensitivity is. That's referring to the smallest signal which can result in acceptable signal-to-noise ratio at the output. Right? And then selectivity. Selectivity is really a code word or a way to cleverly talk about filters. And we're concerned about selectivity in receivers because we typically are not the only users of the spectrum. Our spectrum is typically cluttered with signals. weak signals, which are nearby, which can cause problems. Strong signals, which might be very different in frequency, which can still cause problems. Understanding how to deal with the presence of those signals and keeping them from affecting our sensitivity is what selectivity is all about, filtering. Okay, so if this is what a receiver is all about, then we really have boiled this down to two issues. One is, what does the antenna provide to the receiver? And then what does the receiver subsequently need to deliver to the detector? Well, my answer to this is usually the opposite of what most people would think of. Most people think of it as antennas as being ways to capture signals and deliver them to the receiver. After all, this is what we're interested in. I think most savvy receiver designers do not think of it in those terms. They ask themselves, what is it from the outside that limits my sensitivity? And that's really the way I tend to think about receiver design. What is it that the receiver sees other than a signal that affects sensitivity? In one word, what is that?
Noise.
Noise, of course, noise. So I'm talking about noise, which is external to the antenna, which is captured by the antenna. What things could we be talking about here? The easy one is man-made noise, so I'll give you that one. Right, so this is everything that human beings do that create broadband noise, typically. Car engines, digital clocks, digital signals produce high-frequency content. You add all that stuff together, you get a noise-like spectrum, which is part of what the antenna captures. Two more important contributions in microwave receiver design. Anybody have an idea? Two other important noise sources.
Atmospheric noise.
Okay, I would say, let's call it celestial noise. Yep, so what you get when you look up, right? And actually, I will tell you, although it takes a little bit of explaining, this is about 99% dominated by galactic emission. The emission, the emission due to relativistically accelerated electrons throughout the galaxy adds up, and we see this. I'll give you some idea of what these numbers are in a moment. What's the third one? Yeah.
Temperature.
Temperature of what?
The channel, the earth.
The ground.
Yeah.
Or you might say more generally the surroundings. Yep, or as I like to say it, looking up, looking down, looking side to side. All right? So these are the things that an antenna will receive that will ultimately limit the sensitivity. After all, if we don't have these things, if we have no noise, we are, in principle, having infinite or perfect sensitivity. If we have no noise, then there's nothing getting in the way of having a suitable signal-noise ratio at the output. So to understand these things, receiver designs, and especially microwave receiver designers, tend to think of this in a kind of a crazy way, and that crazy way is antenna temperature, which I'll abbreviate as TA. Antenna temperature is just a clever way to talk about noise, power, spectral density, which has units of what? Power spectral density, 2704?
dBm per hertz.
dBm per hertz. That works. Let's simplify that a little bit. That's watts per hertz. So dBm per hertz is 1 milliwatt relative to a hertz, or 1 power spectral density relative to 1 milliwatt per hertz. Okay, so antenna temperature is related to this quantity, the noise power spectral density. In fact, they are the same exact thing. Let me explain what this is. So here is one way to think about what an antenna does. All right, if I just show you that, what do you call that thing? That is a Thevenin equivalent circuit. That is a Thevenin equivalent circuit for a receiving antenna. If you want some more details, that's the dot product of the receiving incident field with this thing called the effective length, which describes the polarization and gain of the antenna. And this is the effective impedance of the antenna. So this is just a Thevenin equivalent circuit for the receiving antenna. We like Thevenin equivalent circuits because they let us use circuit theory. Right? Then I can imagine my receiver. and I will model my receiver in a very simple way. I'll just say it's some load. If the particular load value I choose is equal to the conjugate of that impedance, what happens? What's special about that impedance? That maximizes power transfer, right? So what intended temperature is, TA, it is some constant times, what the power spectral density is I'm delivering here is some constant times the intended temperature under the special condition that I have maximized power transfer. So as a quantity which is independent of the design of the receiver. What we just say is, for this particular antenna, if we maximize power transfer, then the intended temperature tells us the power spectral density we get. I mean, just a units check here. This is watts per hertz. This is Kelvin. What is that thing? Anybody know? Yeah. That is Boltzmann's constant, also known as 1.38 times 10 to the minus 23rd joules per Kelvin. Right? You can again do a units check here. I'm converting kelvins to watts per hertz, but joules is the same as watts per hertz. You can see that because 1 joule is a watt times a second, right? Which is the same as a watt over 1 second, and that's hertz. So this all makes sense dimensionally. And for now, there's nothing profound about the use of this constant. I could really use any constant, but it's kind of convenient to define things this way because in a moment, I will start talking about losses. When I start talking about losses, it will be really convenient to use physically based relationships between these things. Otherwise, for all you know, I could make that any constant and I'm just trying to establish some definition. Okay, so I come back here to the things that create noise for me. Well, I would argue, or I would point out that for microwave receivers, typically we see TA on the order of maybe 10K at the minimum, maybe up to 500K or so. Those would be typical power spectral densities that are delivered by the antenna to a perfectly matched input, receiver with a perfectly matched input. Typically celestial noise somewhere between 10 Kelvin and 100 Kelvin. The surroundings, again, somebody mentioned temperature as what this thing was. This is the ground and structures around us radiate noise simply because they have electrons. The electrons are jittering around, and the amount of radiation that power spectral density they radiate is related to their temperature. For that reason, it's typically 100K up to maybe 300K. 300K would be above room temperature. That's about as hot as you'd imagine something getting. And then, but it's typically smaller for a whole bunch of reasons, including mapping polarizations and so on. So, you add these things up. Noise is very hard to kind of bound, but it could go from near zero, if you're out in the middle of nowhere or in space or something like that, to relatively high values, thousands of Kelvin, depending on what else is going on around you. But typically we plan for intended temperatures in this region. Of course, this isn't exactly what the receiver gets, right? In other words, we say this is what the noise is arriving, and this is how we figure out what the power spectral density is. But there's one more thing now that we need to kind of understand to figure out how much noise actually makes it to our receiver. And what's that? Well, it's related to this, right? The antenna temperature assumes that the receiver is perfectly matched to the antenna, right? If you take my course in antennas next semester, you will find out how incredibly difficult this is to achieve over any significant bandwidth. And so what you find out is that there's always an impedance mismatch there. So what you've got is a scenario in which here is the antenna, here is a receiver, which typically has a fixed input impedance, I can call it Z in this case. And when I look into it, I see a reflection coefficient, a voltage reflection coefficient, right? And you know from 3106, that voltage reflection coefficient is going to be Zin minus ZA, Zin plus ZA, that's the voltage reflection coefficient. So how much power available at the antenna into a conjugate matched load actually makes it into the receiver. Well, I won't torture you with trying to remember 3106 stuff, but it's that much, right? This is how much power makes it across that impedance mismatch. I'm sorry, that's how much power is reflected from the impedance mismatch. So this is how much power is able to traverse this impedance mismatch. So if it's perfectly matched, I get all the intended temperature. If it's imperfectly matched over some part of the bandwidth, I get less. And the amount it's less by is this factor. Okay. It's fun, these are power spectral densities. It's convenient to think in terms of total power sometimes. So we should know something about the bandwidth of these signals. Typical bandwidths depend on the applications. I've listed a bunch of applications there. I would say generally, very generally, maybe on the order of 1 to 100 megahertz. Typically, you're wasting your time if you send less than 1 megahertz of these frequencies because there's lots of bandwidth available. There's technical reasons why it becomes difficult to send more than 100 megahertz at a time, although it's certainly possible. So most of the applications fall in this range. So you can figure out the total power. What am I calling this here? I don't give a name. The total power is just PSD, power spectral density, times bandwidth. Right? So you can see that that's going to be somewhere between what the values I'm using here. Let me do it this way. So here's an intended temperature, TA, power spectral density, K, TA. I can work out this value for one candidate power spectral density, or one intended temperature. Let me just say 290K, right? Just for the purposes of getting a power spectral density to work with. So the power spectral density associated with the intended temperature of 290K, which is right in this range here. That turns out to be, I should know this number by heart because I use it about 10 times a day. 3 times 10 to the minus 21 watts per hertz, right? Somebody mentioned that power spectral densities are often expressed in terms of dBm per hertz. So that's, anybody know what that is? Somebody usually has had an internship where they've messed around with these kinds of things and knows this number. It's very close to minus 174 decibels relative to millowatts per hertz, or as has been stated, minus 174 dBm per hertz is a weird way we often abbreviate that idea. So minus 174 dB relative to 1 milliwatts per hertz is a typical then power spectral density that we get associated with the intended temperature in this range. So now if we come back over here, right, we've got minus 174 dBm per hertz, and the total power is greater by the bandwidth. That bandwidth is somewhere between 60 dB and 80 dB. Right? So if we take the high end, say 100 megahertz bandwidth, right, then we get minus 94 dBm as the power, which is being delivered. Right? And that's at most. Right, because we know that we have this thing going on, and this could be less. I really should say at most, but that's typically a high value for 100 megahertz. So now we know something useful for receiver design. We know that that's a typical kind of input power that we might deal with, even if there's no signal. So I'm just working out what kind of power levels I expect to see at the input of the receiver, even when my signal of interest isn't present yet. Right?
So is that why it's just the noise floor?
You might call this a noise floor, but noise floor is typically an idea that's best applied to the receiver self-noise, which I haven't gotten to yet, but it's the right idea. If this is the power that's present due to just external noise in the environment, already the sensitivity is limited, right? For example, if we want to achieve a signal noise ratio of 1 at the input of the receiver, what's the signal power have to be at this point? Same, right? I mean, signal noise ratio 1 means that the signal power is equal to the noise power. So it's sometimes said that the MDS, which is an acronym, minimum discernible signal, is, in this case, would be minus 94 dBm. In other words, it would take a signal power of minus 94 dBm in this bandwidth of 100 megahertz to achieve a signal noise ratio of 1 at the input. Right? Is that the signal noise ratio we expect at the output of the receiver? Probably not, right? Because we know the receiver is going to contribute some noise. So we're going to circle back to that idea in a moment. But this lets us do something. The first criteria here was gain. And we have to decide how much gain we need, right? So this lets us bound the amount of gain we need because, what we should be able to do is raise this level up to some level which is useful to the detector or the ADC. So the next thing we have to decide is what should the receiver be able to deliver to those detectors? Anybody got a theory about that? It's actually a very simple idea. Well, the way to work that out is to ask yourself, what kind of signal levels do detectors and ADCs like? What do they like to see? I'd ask you to do this if I were teaching this course. I'd make you go look up a whole bunch of A-to-D data sheets and figure it out. At what levels do A-to-Ds typically clip? You will find that almost universally, they clip on the order of about 1 volt peak to peak in the 50 ohms. 2 volts peak to peak into 100 ohms differential, same thing. You also find that for most detectors, like diode detectors, envelope detectors, things like this, guess what level they like to work at? They tend to work optimally, some compromise between sensitivity and dynamic range. Also on the order of 1 volt peak to peak in 50 ohms. The reason for this is a little bit subtle. It's fun to talk about, but we don't have time. But I can give you a clue, right? For a diode detector, if you use regular silicon technology, what voltage do you need to switch between forward bias and reverse bias, forward bias and unbiased? What voltage do you assume when the diode's forward biased?
0.7.
0.7 of a volt, right? 0.7, there you have it. That's on the order of 1 volt peak to peak. If you're using an envelope detector, you need to see that signal swing the diode from forward biased to firmly reversed biased, which means it has to swing around 1 volt peak to peak within an order of magnitude or so, right? This is one example. I'll tell you, generally, it's a pretty good assumption to assume that whatever's coming out of the detector will be well served if it arrives at this level, right? Maybe a little bit higher, maybe 2 or 3 orders of magnitude lower. For example, if I use an A-to-D with lots of bits, I don't necessarily have to clip the A-to-D to make it work properly. I could just toggle a few bits at the bottom. So that number is, that's why I had the O in the parentheses. It's order of magnitude. And really I could get away with an order of magnitude lower, but this is, we're just trying to figure out in broad strokes what we can do here. How much power is that? Well, this power is what? It's 1 volt peak to peak. The equation for power is what? V squared over R. Is that right?
Yeah.
All right, is that peak to peak? No, that's
RMS.
right? So what's 1 volt peak to peak in RMS units?
Root 2 over 2.
Yeah, 1 over root 2. Right, squared over 50 ohms. I haven't done that calculation in probably 10 years, but I'm reasonably certain it's 10 milliwatts. Also known as plus 10 dBm. So we find that almost all receivers have some ability to deliver power, typically on that order, on the order of plus 10 dBm. So guess what we have just done? We figured out the gain of a receiver. It should, in this case, using the numbers I've come up with, move minus 94 dBm up to plus 10 dBm. Right? That's the gain that I need. How much gain is that? That's plus 104 dB. So that would be a pretty aggressive receiver design. Like I said, it could be 2 or 3 orders of magnitude less. So maybe it's only 94 dB or maybe it's only 84 dB or something like that. Yeah.
So if it's 1 volt peak to peak, you should have like 2% out of peak and then the rest of the number like RMS.
Well, RMS is 1 over 0.7071 times the.
That's peak to peak, but don't you want the peak?
Oh, I'm sorry, yeah, when I say peak to peak, I should really say peak to, or peak,
Okay.
right, just magnitude. Yeah, I'm sorry for being confusing about that. You're absolutely right, that would be, what, half a volt peak to peak or whatever. Good point. That's, in my defense, I'll just point out, I put order of magnitudes around everything, but you're absolutely right, thank you for pointing that out, I should be more careful with my notation. Okay, so, 104 dB gain, maybe down to something like plus 84 dB, if, you know, I'm using, for example, the A to D with lots of bits, where I don't have to necessarily clip the A to D or get close to clipping to make it work properly. So now, we can start working out some other details. So for example, anybody know for a single transistor amplifier, an amplifier consisting of one transistor stage, what kind of gain can I get out of it? 20 dB would be pretty high, right? That's on the high end. Typically 10, 15 dB for, we take into account most other things. Again, simple physical arguments for that, but it turns out that you can pretty much assume that it's going to be difficult to consistently achieve a gain per transistor stage of greater than 15 dB or so. Right? We also know we're going to have some losses in here. So I just worked out, let's see how did I work this out. I said, I use, let's see, 74 dB gain. Right, so that's giving myself 30 dB of margin over here. And then if I say, well, I really need 10 dB for losses, right, which I haven't accounted for yet. And then if I have transistors that have 15 dB per stage, now this calculation tells me how many transistors I need, right? So it's something like 6. You can't have a partial transistor, so I'm reasonably sure it's something like 6. Right? Now again, maybe this is 7 transistors, maybe you can do it in 4 transistors, but you're going to have on the order of that many transistors for any microwave receiver you can imagine, just for the reasons that I've kind of framed here. Now I've got a whole bunch of variables here. Like I said, we can have A to Ds as opposed to single detectors. This level could go up or down depending on these 2 orders of magnitude and bandwidth variation I've got here. So things can vary over 20, 30 dB easily. How do I accommodate that? All receivers must deal with this, by the way. How do I accommodate it? Do we have an idea? I mean, I'll help you out. The gain has to be variable. So what mechanisms can we use to make the gain variable? AGC, right? It's called automatic gain control. So typically some fraction of these transistors are invested in amplifier stages, which the gain can be varied. Right? You might also consider using more gain than you need, and using some attenuation that's variable. That's another approach. Or you might consider using A to Ds, again, with lots of bits, so that you can accommodate a lot of signal swing just without changing the gain at all. Okay. So, consider nothing but the receiver cell, the external noise, but we know that this thing is also going to create noise, right? So the scenario has become this. Here's my receiver, here's my antenna. I've got an antenna temperature coming in. That's been modified by the impedance mismatch factor. Up to now, I've just been assuming it's